So we don't get bored with just limiting our worlds to looking at square roots. Now we're going to take a look here at this example, cube roots, and this fifth roots. So in the world of looking for cube roots, in terms of the variables, we're going to look for powers of 3, or another way to say that is exponents that are divisible by 3. So let's take a look here. Starting at 40, let's see how we are able to factor this cube root. 40, and I think we've looked at this in a previous example, we can factor 40 8 times 5. Why 8 times 5? Why not 2 times 20? Because 8 is a perfect cube. So we're going to be able to take that out of the radical. Now moving on to our x, we have x to the 10. 10 divided by 3, aren't able to do it without a remainder. So same as before, we're going to start to go down by 1. So 10, go down by 1 to 9. Yep, 9 is divisible by 3, so we can use that version of the 9, of the x. And now we need x to the first power, because remember we have x to the 10 here. Moving on to y to the 14. 14 divided by 3, again, can't be done without a remainder. So let's start to factor. Go down by 1, 13. 13 divided by 3, Go down another one, 12. 12 divided by 3, yep. So now we have y squared here because we went down by 2. 14 would be y to the 12 times y to the 2. 12 plus 2 is the 14. I think I will do what I did with the previous example, and that is collect all the perfect cubes in one radical, and then what the other is in the back radical. So here, 8 is a perfect cube, and then 5 is not, so I'm going to put that there. X to the 9 is a perfect cube, so I'll put that here. X is not, so I'll put it in the back. Y to the 12, perfect cube, I put it here. Y squared is not, I'll put it back here. Now I can take my perfect cubes. Cube root of 8 is 2. 9 divided by 3 is x to the 3. Be careful here. You divide by the 3. We're taking cube roots now. And then 12. 12 divided by 3 is 4. So that is what's sitting outside the radical. And now this cube root 5xy squared just sits. There's no further simplification that can be done there. Next example, we have fifth root. So we're going to be looking for exponents that can be divided by 5. I'm going to change colors here. So let's take a look. 32, as it turns out, 32 is 2 to the power of 5. So that's a power, that's a perfect power of 5. So I'm going to leave the 32 there. Now, x to the 12. 12 divided by 5, can't do it cleanly. So go down 1, 11. 11, nope, can't divide that by 5. 10, yep. So we have x to the 10. And then the 2 that we went down by, there's our 2 factors for x. Moving over to y squared. Can't divide that by 5, fraction, and being that 2 is less than 5, we are not going to be able to simplify that, so it's just going to sit. Z to the 8. Can't divide 8 by 5, go down 1 to 7, nope, go down 1 to 6, nope, go down another 1 to 5. 5 divided by 5, yep, can do it. So we have z to the 5, and now we went down 3, so we have our z cubed. Remember, when you have factors of a variable, when you multiply, you add the exponents, and these should always give you what was sitting under the radical initially. So to be consistent here, let's collect the perfect powers of 5, and then what will not be able to be simplified. So 32, yes. X to the 10, yes. X squared, no. Y squared, no. Z to the 5th, yes. Z cubed, no. Now taking our perfect fifth roots, 32, the fifth root of 32 is 2, and you can do these on your calculator, so make sure you know how to do them. X to the 10, 10 divided by 5 is 2, so we have x squared, and then z to the 5th, 5 divided by 5 is 1, z to the 1 or just z. And then the information in this radical just sits. There's no further simplification that we can do.